Welcome to the second lecture video in Physics 10 in 30 lectures. We begin our study of physics with study of motion, kinematics. In kinematics, we are not quite covering laws of physics yet, but the precise language we will develop in kinematics will help us when we start studying causes of motion in dynamics in a couple weeks. We start this lecture with the first part of Chapter 1 overview, covering terms, definitions, and conceptual ideas in kinematics, leaving more quantitative details for the second part in the next lecture next week. I'm trying something new with Google's NotebookLM, and the second section in this lecture video will be an overview video generated by NotebookLM. Do watch it through and let me know whether you felt it was helpful. I'm happy to use generative AI when it helps you learn. I can also do something else when it doesn't help you learn. The next two sections are intended to help you distinguish ideas and words in motion that I've seen people confused by in the past. One is in distinguishing acceleration and velocity, and how the motion we feel is different from motion that we see in velocity. And the next and the final section in this video set illustrates one of the simulations from PhET, PHET.colorado.edu. As a tool you can use to help gain a solid conceptual understanding of quantities in motion. We will go deeper into motion graphs and cover the more quantitative details in the next lecture, and wrap up next week looking at some examples of motion in 2 dimensions, including projectile motion. Please watch the Chapter 1 overview, Part 1, coming up next. Hi, this is the overview video for Chapter 1, Kinematics. Part 1. I'm gonna break up this overview into 2 parts. In this part, we'll talk about just what we'll cover in Lecture 2 this week. And in the next overview, Part 2, we'll cover what we'll cover in the next lecture next week. So, kinematics. We call it study of motion. And we add the part without causes to distinguish it from what we'll look at in the next chapter, dynamics, which deals with the causes of motion. So for this chapter, this week and next week, all we are looking at is motion itself. Without worrying about what's causing it, we're just looking to describe motion as precisely as we can, both qualitatively and quantitatively, using precise language. So one of the first things we'll do is we'll introduce this precise language. We're going to define some words, some of which will align fairly well with your everyday intuition about these words, like position describes where something is. So often it's as a function of time, and that I think is intuitive enough. And we introduce the word displacement, which might sound a little bit fancy, but displacement, it's change in position. And one thing I want to highlight from the beginning, it's a vector quantity by which we mean we care about its direction. And we'll often indicate the direction with a sign. I'll talk about that more in a little bit. And distance, even though in everyday English language, it would be a synonym for displacement, in physics, we're going to take care to distinguish displacement and distance as 2 distinct words that mean 2 different things. The main distinction is that displacement is a vector, we care about the direction, and distance is a scalar. We don't care about the direction, we only care about the magnitude, the size of displacement. And I want to highlight the word distance traveled and just say, even though in, again, everyday English, distance and distance traveled might mean the same thing, we're going to distinguish them right now to say that distance traveled in this chapter, in this class, doesn't mean the same thing as distance. The main distinction, so we say distance traveled is total length of path traveled, and the best example to think about is a round trip. In a round trip, when you go from point A to B, come back from B to A, your total displacement will be 0. Change in position is 0. You came back to your original point. So your distance for that round trip is 0 because absolute value of 0 is 0. But the distance traveled won't be 0. You count all the lengths. And in the more quantitative treatment of kinematics, we don't really use the distance traveled. If we have to, we'll break up the trip into different segments. And but when you see the word distance traveled, read it carefully and make sure you don't mix it up with the distance. And finally, time. Well, time is time. I think we all have intuitive sense of time. And these quantities are measured in SI unit system in meters and seconds. So those are the words that we introduce to describe motion precisely in terms of position, and everything else is derived from that. And as we talk about velocity and speed, we want to make sure to highlight the distinction between vectors and scalars. The main thing is vectors have direction. So some of the words that we will appropriate for physics, we're gonna designate them as the vector quantities. Displacement is a vector, velocity is a vector, meaning both of these quantities, when we mention them, we care about direction. And scalar is the kind of quantity where direction doesn't matter. Some quantities are naturally scalar, like temperature. Some of the scalar quantities are, they come from a vector quantity. Distance is the absolute value of displacement. It's the displacement without the direction. That's a distance. And speed, even though in everyday language, that's synonym for velocity. In this physics class, we do this weird thing where we take everyday language, give it our physics meaning to it, and we are going to insist that you use it. So speed is the scalar version of velocity. So speed and velocity are not the same thing in this class. Velocity, when you hear that word, just remind yourself that direction matters. And when we talk about speed, it's when we have removed the direction information. We took the magnitude, we took the absolute value, and that's what speed is in this class. I know in everyday language, speed and velocities are synonym, but we need different words to distinguish the speed, scalar version of velocity. That's why we do what we do. Finally, the coordinate system, that's very important when you are talking about motion, kinematics in a quantitative way. This is conceptual physics, so we are going to be as light on math as possible. So oftentimes we'll deal with the motion in 1D. The one kind of exception is when we get to projectile motion, that'll naturally have to be 2D. In 1D, the coordinate systems are simple. It's basically a number line. And so we define which direction is positive. Oftentimes we say rightward is positive or upward is positive. Then the negative would mean the other direction. So leftward is negative, downward is negative. And you can flip them around. The main thing is to be consistent. So in some problems, it's convenient to define downward as positive. It's fine as long as you're consistent and don't confuse yourself. So we introduce vector scalar coordinate systems because in the next quantity that we'll talk about, velocity and speed, which is derived from position, we distinguish between those different quantities, one of which is a vector, the other is a scalar. So we want to make sure to keep that distinction in mind always. So average velocity, it's derived from displacement, position. It's simply displacement divided by the duration of time of travel. It's measured in what you would expect, meters per second. This is in meters, this is in seconds. So yeah, meters per second. And instantaneous velocity, this is an idea that we spend more time with in calculus-based general physics. Really, to go from average velocity to instantaneous velocity, that's where you need a calculus step of making this delta t infinitesimally small, very, very small. And this being conceptual physics, we won't spend a lot of time in it, other than to say that instantaneous velocities are really nice to work with, especially later on when we look at causes of motion. And instantaneous speed, very nicely, very simply related to instantaneous velocity. It's simply the absolute value of the instantaneous velocity, magnitude of instantaneous velocity. And I want to give a caution to the word or phrase average speed, which is not going to be the same thing as the simply the magnitude of average velocity. I know it's very confusing because average speed is the distance traveled per time. And if we're looking at magnitude of average velocity for example, round trip, average velocity for round trip is 0 because your total displacement is 0. Now your total distance traveled is not 0. That's why average speed won't be 0. If you drove from point A to B at 60 miles per hour, go back from B to A at 60 miles per hour, your average speed of travel is 60 miles per hour. Very intuitive, very simple. That's how you would talk in everyday situations. But in the context of this class, I want to make sure that that kind of intuitive everyday meaning of average speed, which we are not changing, is confused for the magnitude of average velocity. This is, I guess, where I say instantaneous quantities are nice. You know, magnitude of instant velocity is the instantaneous speed, but the magnitude of average velocity is not average speed. And I think so in most quantitative descriptions of kinematics, we simply avoid the use of the word average speed. So we'll just deal with instantaneous quantities. Finally, we have acceleration. That's the last section we'll cover in this overview in this lecture this week. We'll deal with the more math heavy portion next week. Acceleration is derived from velocity. In a similar way, velocity was derived from displacement. Average acceleration is the change of velocity. Remember, velocity was change of position, displacement per time. Acceleration is change of velocity per time. Acceleration is a vector quantity, and we don't have a word that just means the magnitude of acceleration. You'll have to look at the context. If you just hear the word acceleration, assume that direction is involved. So sometimes in everyday context, people talk about deceleration. I myself will avoid that word. I'll just say acceleration, sometimes say the word negative acceleration, which means acceleration in the negative direction. And you kind of want to look at the coordinate system and be careful what is precisely meant by that. Instantaneous acceleration is again derived in a similar way instantaneous velocity was. You take the average acceleration, make the duration of time really small, infinitesimally small, that becomes instantaneous acceleration. And this will be very important later on when we talk about causes of motion in dynamics. And because acceleration is a vector quantity, change of direction also can be associated with acceleration, even when there's no change in speed. There's a particular type of motion where you will see that circular motion. And slowing down, or what sometimes people call deceleration, that requires a opposite sign to velocity. So if your velocity is already in the negative direction, then quote-unquote negative acceleration actually means speeding up, not slowing down. So those are all context dependent. So that's the last section that we'll cover in this overview. The next two sections, more kind of quantitative, mathematical part of it. We have another lecture set aside for that, so we will deal with it in the next lecture. We'll talk about that more in the next overview. So let me hide this. For this coming lecture, what's most important is sort of qualitative descriptions of position and displacement, velocity and acceleration. We have some extra time in this lecture set, so I want to try something new. In NotebookLM, with the sections that we are covering in this lecture, I generated an overview video in NotebookLM Studio. And I watched through it. Some approaches are not exactly the way I would have done it, but I didn't see any serious mistakes in it. And it does look like it's a drawing from the content of the textbook. So I want to just present it to you without further commentary. See if it's useful. Let me know. If it's useful, I will continue to do it. If this AI generated video bothers you, then let me know. I will take it out in the future, or at least to do less of it. Thank you. Without further ado, here's the AI generated video.
Hey there and welcome. Today we're going to get you fluent in a brand new language. No, not Spanish or Japanese. We're talking about the language physicists use to describe pretty much everything that moves, from a planet zipping through space to a car on the highway. This is the language of motion. Let's jump right in. I mean, just look at this kestrel. It's hovering, it's diving, it's constantly changing direction. We see motion like this all around us every single day. But if you had to describe it, I mean really describe it with precision, how would you do it? How could you predict exactly where that bird is going to be in the next second? That's the big question we're going to tackle today. The field that gives us all the tools for this is called kinematics. It actually comes from a Greek word meaning motion. Now, the really crucial point here is that in kinematics, we're only focused on describing the motion. We're not, for now, worrying about what's causing it. We're not talking about forces or engines or muscles just yet. We're just being detectives, observing and describing what we see. I absolutely love this analogy. If motion is a language, then kinematics is its grammar. It gives us the rules, the vocabulary, the structure. And once you know that grammar, you can describe any motion in the entire universe, from a tiny ant crawling on the ground to a massive galaxy hurtling through space. So where do we even begin? Well, we start with the most basic, fundamental question of all. Where is something? Let's build everything up from there. To tell someone where an object is, you need a starting point, right? Physicists call this a reference frame. So for this professor, her position, which we can just label X, is being measured from the edge of that whiteboard. She starts at one point, 1.5 meters, and she ends up at another, 3.5 meters. Pretty straightforward. Now, when her position changes, we give that change a special name, displacement. See, it's not a single location, it's the difference between where she ended and where she began. The calculation is super simple. You just take the final position and subtract the initial position. So for her, that's 3.5 minus 1.5, which gives us a displacement of positive 2 meters. But here's where that grammar starts to get a little tricky, and it's a super common mix-up. You're probably thinking, okay, displacement, isn't that just a fancy word for the distance you traveled? It seems like it should be, right? Well, let's put that idea to the test. Let's imagine this cyclist. She starts out, rides 3 kilometers west, then stops, turns completely around, and rides 2 kilometers back to the east. Let's break down that little trip. Okay, now look at this. The total distance she traveled, that's easy. It's the whole path she took. 3 kilometers out plus 2 kilometers back. That's 5 kilometers. Simple. But her displacement, that only cares about the difference between her final spot and her starting spot. If we decide that west is the negative direction, she went minus 3 kilometers, then came back plus 2 kilometers. Her final displacement is minus 1 kilometer. See? They are totally different numbers. So why? Why are they different? The answer lies in one of the most fundamental, most important ideas in all of physics. Let's get into it. Some things we measure, like the 5 kilometers our cyclists traveled, are what we call scalars. A scalar is simple. It just has a magnitude, a size. It's just a number with a unit. How much? 5 kilometers. That's all the information it gives you. Displacement, on the other hand, is a vector, and vectors are a bit more sophisticated. A vector has both a magnitude and a direction. It doesn't just answer how much, it also has to answer which way. So the cyclist's displacement is 1 kilometer, but in the westward direction. That little negative sign is the piece of grammar that tells us the direction. And this chart just lays it all out perfectly. You've got these two families of measurement. On the left, you've got your scalars, just a number. Things like distance, speed, time, even temperature. On the right, you've got your vectors, a number and a direction, like displacement, velocity, and acceleration. Getting this difference down is absolutely crucial. So now that we have this powerful new idea, the difference between scalars and vectors, let's use it to clear up another classic pair of terms that people, including me sometimes, use interchangeably: speed and velocity. So what's the real difference between them? Well, it all comes down to their definitions, their formulas. If you look at average speed on the left, it uses the total distance you traveled, which we just learned is a scalar. So that makes speed a scalar. But average velocity on the right, it uses displacement. And since displacement is a vector, that means velocity has to be a vector too. It has direction built right into it. Let's make this totally crystal clear with an example I guarantee you've experienced. A quick round trip to the store. You leave home, go to the store, and come right back. Okay, let's run the numbers on this 30-minute trip. The total distance you traveled was 3 kilometers there and 3 kilometers back. So 6 kilometers. But what was your displacement? Well, you ended up exactly where you started, back at home. So your change in position is 0. And this leads to a really wild result. Your average speed for the trip was 12 kilometers per hour, but your average velocity was 0. How crazy is that? All right, we've covered where you are and how fast you're going. But what if that is changing? This brings us to our final core concept in our toolkits: acceleration. By definition, acceleration is the rate of change of velocity. And notice that word, it's velocity, not speed. Since velocity is a vector with both speed and direction, you can change your velocity by speeding up, slowing down, or just by changing the direction you're going. Any of those changes, even just turning a corner, means you are accelerating. This train is a perfect example. It's moving forward, so its velocity is obviously forward, but it's slowing down to a stop. For that to happen, its acceleration has to be pulling in the opposite direction of its motion. So right away, we see that acceleration isn't always in the direction an object is moving. And this leads us to another really common trap. When we hit the brakes in a car, we slow down, and we sometimes call that deceleration. So it kind of feels like negative acceleration should always mean you're slowing down, right? Well, not always. Think about it this way. The rule is if your acceleration is in the opposite direction of your velocity, you slow down. But if it's in the same direction, you speed up. So if you're already moving backward, if you have a negative velocity and you have a negative acceleration, you're actually going to speed up in that backward direction. And there it is, our complete, fundamental toolkit for describing motion in one dimension. We have position, which tells us where something is. We have displacement, which tells us its change in position. We have velocity, which tells us how fast that position is changing. And we have acceleration, which tells us how fast the velocity is changing. So we've basically mastered the grammar of motion. We've learned the how. But that leaves us with this one huge nagging question. Why does velocity change? What is it that causes an object to accelerate in the first place? Well, that is the next step in our physics journey, and it's a fantastic story all about forces.
Hi. In my experience in teaching physics, most people have a great intuition for velocity. If I tell you that a car is moving at a speed of 60 miles per hour in a direction to the east, for example, then you know intuitively what that's like. You even know what it feels like. That's what I mean. A lot of people have great intuition for velocity. It's acceleration we have to distinguish more carefully from velocity. So let's start with the definition. So acceleration is defined as the rate of change of velocity, or using symbols to express the same idea more succinctly, we would say acceleration is equal to how much velocity changes in a given amount of time. And if we are being picky, we need to be careful about velocity being a vector It has direction. So acceleration is also a vector. It has direction. So the definition is all well and good. The problem here is that a lot of physics students initially don't have a good intuition for acceleration. So you can memorize this definition, but it takes some time for you to internalize this definition. And here's why this distinction is important. Velocity and acceleration are how we describe motion. But when we say motion, the idea of motion is quite not precise enough. One thing you can see is that both the velocity and acceleration are somehow involved in motion. What we now have to carefully separate is different parts of motion that you have a instinctive, intuitive connection to, and how those different parts are related to acceleration and velocity. I think here's one useful statement to make. Acceleration is how you feel motion. We'll see that in a little bit in more concrete examples. All right, let's just start out with some examples. I think it'll be useful to start out with an example where there is motion, but you don't quite feel it. A good example of that is an airplane ride. Or if you've never been on an airplane, you can imagine a BART or subway ride. So imagine you are in an airplane. You know that the airplane is moving very fast. A lot of commercial airplanes will be flying at something like, let me make up a number that is pretty close, 700 miles per hour. But one of the strangest thing about airplane ride is that you don't really feel that. Now, if you haven't been on an airplane, then I want you to imagine that you've been on a BART ride. Now, BART doesn't move as fast as airplane. Maybe it moves at, I don't know, 70 miles per hour. Now, maybe you have been on BART and you don't feel like you didn't feel the motion. So this is where I want you to start making this distinction. Imagine the part of the BART ride as the train is moving at a constant speed. It just left the station. It reached the maximum speed of 70 miles per hour. And the next station is a few minutes away, so it's continuing to move at 70 miles per hour. It's that portion of the motion that you don't quite feel it. You only feel that BART is moving when it's beginning to move or when it's coming to a stop. So this is an example of motion where acceleration is 0 and the velocity is not 0. This is what I mean. Acceleration is mostly what you feel in a motion. All right, let me move on to second example where you feel a lot of motion. I guess not many people would have this direct experience, but you can use your imagination. Imagine a car chase. Or you can imagine that you are riding with a particularly aggressive driver who's speeding and changing lanes. Let's say as this car's being chased or chasing, it's weaving in and out of traffic, changing lanes a lot. Then you can imagine what that feels like. You will be jolted back and forth in the car. As it speeds up and slows, you'll be pushed back, pulled forward. You've been in a car, you know what that feels like. Well, maybe not exactly what a chase feels like. You know what the milder version of that feels like. So this is the case where velocity is not 0 because car is moving, and the acceleration is not 0 either because the velocity is constantly changing, and acceleration is given by change of velocity. So as the velocity of the car changes, you have this non-zero acceleration. So for example, at this point, the car had a velocity like this, and at this point, car has a velocity like this. At this point, car has velocity like this. So you can see that even if the car was moving at the same speed, because the direction of its motion is changing, its velocity is changing, and that change of velocity will be associated with an acceleration. And actually, this is a lot closer to our everyday experience. And I think this is why in our intuition, the how we feel motion and which part of the parameter, velocity or acceleration, is responsible, it's mixed up because in most of our everyday experience, it's all mixed up. So intuitively, we don't quite know whether to credit the velocity to our sensation of motion or credit acceleration for our sensation of motion. Now, I don't know how many of you have been to Universal Studio, or I guess there could be other theme parks that do this. There are machines called motion simulators. And what the motion simulator simulates is the acceleration. You can kind of see that from outside. When you look at the motion simulator from outside, its velocity is more or less zero. It's not going anywhere, but it's jerking back and forth and it's tilting. So it's causing acceleration for people inside. And if you're sitting inside, you are looking at the screen, some video that's consistent with the motion you're supposed to be feeling, and it's a very realistic feeling. It's because our sensation of motion is based on acceleration. So I hope this example is helping you realize that when you are feeling motion, what you should look out for is acceleration, not velocity. But it is a fact that so much of our intuition about motion is tied in with velocity. We feel like if something is not moving, velocity zero, that there's no motion happening. So I want to end with the last example where there is no motion in the sense that velocity is zero, but there is acceleration. To crystallize that you can have acceleration with zero velocity. And even though you would be feeling motion at that particular moment in time, the velocity is zero. So I don't really have a good name for this, so let me just call it non-zero acceleration with zero velocity. So imagine you are in a car which is stopped at a signal light. The light is red, so the car's not moving. Its velocity is zero. And since it remains at zero, its acceleration is also zero. You don't feel like it's moving. Now, at time equals zero, the light changes from red to green. And the car starts to move forward. And you feel this motion. If you step on the accelerator, the pedal, hard enough, you will feel thrown backward in the car. That's how you're feeling the motion. Now, this is the question I want you to consider. At time equals zero, when the light just turned green, what is the velocity of the car? It's tempting to say that the velocity of the car is also greater than zero. After all, isn't it moving forward? But what you have to carefully consider is that we are looking at time equals zero. This is the moment at which light turned from red to green. Now, let me do a little bit of math here. I can take this definition here and turn it into a statement about the change of velocity. So the change of velocity is acceleration times duration of time. So before time equals zero, your acceleration was zero. So no matter how long you wait, change in velocity would have been zero. Now at time equals zero, the duration of time over which acceleration was at zero has been zero. That's the exact moment at which acceleration flipped from being zero to non-zero. So what that means is there haven't been enough time for the velocity to have changed. So at time equals zero, velocity still is zero. So this is the first very common everyday experience where you feel the motion, you have non-zero acceleration, but you have zero velocity. Now, what you should notice is that this moment is very fleeting. Another moment, a second, fraction of a second later, your velocity won't be zero. because with non-zero acceleration, as you accumulate change of time, you will accumulate change in velocity. So all these examples will be very momentary, fleeting. Now, let me give you one more example of non-zero acceleration with zero velocity. I have this ball here. When I throw it up and catch it, at the very top of the motion is another example of where it has non-zero acceleration with zero velocity. So let's say at the bottom, I threw it up with a velocity of 5 meters per second. Then about half a second later, at the top, the ball would have a velocity of 0. And then another half a second later, the ball will have come down and it'll be moving downward at 5 meters per second. And this is the rough trajectory of this ball. So at that exact moment, when the ball is at the top, its velocity is 0. I can say that its velocity is 0 without actually measuring it from this argument. If it had positive velocity, it would be moving upward more. If it had negative velocity, it would be moving downward. So by the fact that it's at the very top, its velocity has to be 0 because it's neither moving upward nor downward. And I'm saying that this is an example where acceleration is not 0. Now, how do I know that acceleration is not 0 at the top? Maybe it's 0, like velocity was 0. Well, here's how I can argue that the acceleration at the very top is not 0, even though velocity is 0. It's because of the change of velocity. The moment before it reached the top, the ball was moving upward, so it had a positive velocity. And the moment after reaching the top, the ball will be moving downward, so it has a negative velocity. So because of that continuous change in velocity, I know even at the very top, the velocity is still changing. And because this velocity is changing, that means acceleration is not 0 at the top. So these are some examples distinguishing between acceleration and velocity. And I hope this is giving you enough concrete examples for you to be able to distinguish between these two things, acceleration and velocity, in your own thinking. I will tell you that this is a simple concept once you get it. But until you understand, because there's so much your natural intuition working against this correct distinction, that it'll take effort for you to get it. So if you have any questions that come up, please email me. And one resource that you have that may be useful for you is the pre-Unit 1 discussion questions that you answered. That reflects how much you knew about motion before you started reading Chapter 2. So going back to your answer there, comparing that with what the textbook says about acceleration and velocity, will help you start to clarify what it is that you may not have understood before. And that'll be the beginning of aligning your physical intuition with how we describe our natural world. Hi, in the preceding sections, we have looked at the chapter sections that we are covering in this lecture this week, sections 1.1 through 1.5, and we looked at different words, definitions of displacement, velocity, acceleration, and the distinction of vectors and scalars, and how displacement is different from distance, velocity is different from speed, and acceleration, it's just going to be a one word, so unless we tell you magnitude of acceleration, I would start out assuming it's a vector. So we have covered all those, and if all that made sense to you, then great, good work, and you will have an opportunity to test your understanding in the next lecture next week when we look at a few more quantitative examples. Again, still not a lot of math because this is conceptual physics, but we will use some graphs and do simple math. to make sure that the conceptual understanding is solid. So if all of that makes sense to you, then great. I guess you can skip the rest of this lecture or not. But in this lecture, what I wanted to talk about was and illustrate was what if you feel like you don't fully understand what these different words are covering, or maybe you thought in the past you did, and then you didn't do so well on exam or something, and now you're just worried. What if I thought I understood but didn't? So this is where simulations can be really helpful. It can help you explore different things so that you can kind of test the things out for yourself. There's an organization that's been putting out simulations for a very long time. It's called the PhET, PHET.colorado.edu. It's an NSF funded project. They've been around since when I was a student, so I think they've been around a very long time. They have a whole suite of simulations. I'm going to go to physics. And I looked at the simulation that I wanted to illustrate in this meeting. And so I'm going to filter down to motion. And none of the simulations here were quite relevant to what we are doing this week. Now, by default, so if you are exploring simulations on your own, by default setting, it'll filter down to HTML5 simulations, which are great because these are the kind of simulations that work everywhere. They work on your smartphone, they work on any modern web browser. But because the PhET has been around so long, their best portions of their library are not all in HTML5 already. Some of their Flash simulations they've prioritized converting into HTML5, but a lot of their older classic simulations are Java, and the Java still runs fine, so they haven't converted those yet. And the simulation I want you to work through now is what they call the moving man. It illustrates kinematics in 1D. So let me go here. Now they've still improved the kind of the logistical details of how these are done. It used to be that you had to download the JAR file and have a Java runtime environment on your computer. These days you can just run it right on browser. If you click on this, it'll have an option to download to the older thing still, because Java runtime environment is still around, unlike Flash. Or you can run it in browser. They modified a lot of these to be compatible with what's called a chirp browser, and so it'll just run in your browser. And I've tested on some tablets. This will run in some tablets as well. It didn't run on my phone, but it ran on my Android tablet, and I think it also runs on iPad. So this is how you can access the simulation, and I would encourage you to just play with it. That's the whole point of the simulation. It can give you a sense of intuition for maybe things that were not quite clear in just hearing them or reading them just on words on a page. So these are three knobs. You can kind of take it, move it around. I think position is pretty intuitive, self-explanatory. Even velocity is probably fairly intuitive. Now you might wonder as you move it, like nothing's happening. Like what's going on? It's because with the velocity and acceleration, these are things that happen in time. So right now the simulation is paused. So things that happen over time are not happening yet. You have to let the simulation run for things to start happening. I guess you can record and play back. I don't know how much of that I would use. So you can play with it. So you can have a negative velocity with a man running to left. You can have a positive velocity with a man running to right. And I guess all those are constant velocity motion. I think it's intuitive. Most of people, I hope, don't find it confusing. So the part that I think can be interesting is the acceleration. So I think a constant acceleration motion are uncommon enough that most of us don't experience long periods of constant acceleration motion. So I think it's worth seeing. So imagine the man starts on the left edge of this meter stick or roller, or 20-meter stick, and he has so you know intuitively. Let me zero this out. You know intuitively what positive velocity motion would be like. Moves at a constant speed, and so this being moving at 1.6 meters per second. If we move 20 meters, you can even calculate how much time it would take. All good. Now, what if it's moving with a constant acceleration motion? Let me make it constant acceleration of 1 meter per second squared. Think that is it fast or slow? It's 1/10 of Earth gravity. Well, let's see what that looks like. And yeah, at the beginning he moves very slowly, and at the end he's moving really fast. And I think it's the difference is even more striking when your acceleration is relatively low. Let me do that. So I'm gonna, instead of 1 meter per second squared, which is 1/10 of Earth gravity, I guess that can be a fairly fast acceleration. I think it's fast enough that you would feel it. Let me make it 10th of that. Let me go overboard. So 0.1 meter per second squared. And at the beginning, you might wonder, like, okay, nothing's happening, but you can slowly see the velocity arrow, vector arrow, growing and the velocity increasing. By this point, he's moving faster than that 1.5, 1.6 meter per second, and by the end, he's moving fast enough that he's faster at the end than when I did a constant velocity motion of 1.6 meter per second. And that constant acceleration motion, it's the kind of thing that we don't experience that often. Like when you're driving, you have periods of constant acceleration, but those periods are usually short. Like when you're riding in an elevator, especially if you are on a skyscraper, really tall, well-built elevator, they will accelerate gradually. But even those, the acceleration period only lasts a few seconds. So in this simulation, you can simulate constant acceleration motion and see what that looks like. Let me do minus 0.5 meter per second squared, and you can see what that looks like. Starts out very slow, but then he's speeding up. By the time he gets to the end, he's going to be moving so fast that it's sometimes you look at the beginning and you don't realize how fast he's going to be by the time he's done accelerating. So I think visually seeing it is helpful. Now, there's one other feature of this that can be really useful to illustrate some of the textbook examples. That's the chart. You can actually graph what's happening. So I think in the overview and in the textbook we talked about the difference between average velocity and average speed, and I cited an example of round trip, how you could have zero average velocity but non-zero average speed. So let me just reproduce that example exactly here. I'm gonna have the man start from minus 10 meters so that I have the most amount of time available. I'll show vector and let me make velocity, I don't know, 1 meter per second. Some reasonable. Well, I guess that's a little bit too slow. I think a normal walking speed is maybe 2 meters per second, like that's a brisk pace of walking. So I'm gonna have him walk all the way to 10 meter mark, 20 meters, and then I'm gonna pause. I'll turn his velocity around and have him come back. So let's have him go all the way to 10 meters. That'll take I guess 10 seconds total. And when he reaches there, as it comes to a stop, I will pause the simulation. Okay, pause the simulation. He came to stop here. I'm gonna change his velocity with the pause the simulation. Go back at the same speed, 2 meter per second, but opposite direction. So now it's minus 2 meter per second. So and he's gonna take another 10 seconds or so to get back to the original point. So he's going back. This is his negative velocity. Now acceleration is 0, except there are these little bumps that have to do with those moments of turning around, the moments of this acceleration that happened while I paused the simulation. All right, there it is. So this is a round trip, and this represents 0 average velocity motion, because when you zoom in here, the portions where he had a positive velocity, that's cancelled out by portions where he has negative velocity, and his displacement overall is 0 because he came back to the same point. This is where we would say his average velocity over the 20 seconds was 0, but his average speed, if you imagine taking absolute value of this, so it was 2 meters per second here, and this minus 2 meters per second becomes also 2 meters per second. So if you ignore these little portions where he wasn't moving at all, his average speed was 2 meters per second. So this was the textbook example. You've seen the chart. Now you can do other more fun things. You can imagine, okay, what if his velocity going one way and the other way are different? Let me give you that example. Clear everything. And so I guess I want to still fit it into 20 seconds. So let me have him initially move faster. Let's say 4 meters per second. And then I'll have him move slower, like 1.5 meter per second maybe. So he's gonna first move in the positive direction for I guess 2.5 seconds, is it? No, 5 seconds, because it's 20 meters. So in 5 seconds he'll reach the end. And I'll have him come back at slower speed of minus 1.5 meter per second. I can't do in mind how quickly this will take. Maybe 15 seconds, we'll see. So I don't know. We'll see. I can't do this calculation in my head. So now as it comes back, he's slower. You can see it in the slope. The slope is gentler. You can see in the velocity graph. Velocity graph has smaller kind of absolute value. Acceleration graph doesn't really tell you anything. And when it comes back to the original point, let me pause the simulation and talk a little bit. Now this also represents 0 average velocity motion, because his overall displacement over the whole 18.5 seconds, this is 19, so 18.5 seconds or so, he came back to the same point. So it's a 0 displacement, so 0 average velocity motion. And graphically in the velocity curve, it's represented by what we call area under the curve. So this area here, you compare that with the area between the 0 line and the curve here. Those will have the same amount of the area, one being positive, the other one being negative. They will so cancel out. But when you look at average speed, now average speed will be different, because absolute value, this portion looks like that. When you average these two portions, you'll get some number between 1.5 and 4, probably closer to 1.5 than 4. So this is another example of 0 average velocity, non-zero average speed of motion that you can visualize and look at. And let me end with a round trip motion that includes non-zero acceleration. Not like this, but like a non-zero constant acceleration. So let me clear everything, show acceleration vector. So let me see, I need to figure this out. I think if I do 1 meter per second squared, it'll be too fast. Let me try 0.3. Let's see how that works out. I'm gonna stop the simulation when it gets to the end, and then I will turn the acceleration around, having come back. So acceleration is really tiny. Let me zoom in here. And the velocity starts out slow, but as it goes faster, you can see the value of velocity increasing. and the position curve does this thing that looks parabolic. Okay, that might not be fast enough. Let's see. So now we'll have him turn around, have acceleration be that was his last acceleration. I think I had a 0.3 initially, right? So I'll do minus 0.3. That's his acceleration now coming back from 10-meter position. And he's again starting slowly. And as he speeds up, you can see the velocity increasing or decreasing. Speed is increasing. Velocity is becoming more negative. This is where the decreasing can be a little bit confusing because speed is increasing. I think that's a lot clearer. Yeah, that's it. Can I move the maybe this? No. Oops. Yeah, I don't know how to zoom the horizontal portion of the graph. But if you can kind of imagine, let me redo it. Let me do it faster. So let me do it with a 0.4 meter per second squared acceleration so that the whole thing will fit. 0.4. Okay. No. And this time, I think I'm gonna let it come to a complete stop before I stop the simulation. So I'll let acceleration come to 0 before I stop it. Okay, acceleration is now at 0. Let me do minus 0.4 to come back at the same accelerating motion. And this is the kind of the constant acceleration motion, what it looks like visually here, and what it looks like in the graph here. Position curve looks like a parabola. You're gonna see some parabolas as we do projectile motion next week. So yeah, this is the main value of simulation is that you can play with it yourself. You can try different things that I haven't done. I just wanted to illustrate some of the possibilities. And this would be another example of zero average velocity, as in he came back to the same point, so his total displacement was 0, but non-zero average speed. So to figure out the average speed, you'll have to kind of get the area under the curve here, the triangle, area under this triangle here, but take the absolute value and then divide it by 20 seconds. That'll give you the average speed. So I hope this is helpful for those of you who maybe didn't feel comfortable with the language of the kinematics. You can play with it yourself. You can move the man around, and I think this actually does this. So if the simulation is running, I think this actually plots the things out in real time. So yeah, you could just drag him around and do the graph thing like a graph for him. Yeah. Now, if you're doing it this way, the acceleration is gonna look so messy. But velocity, you can kind of try to keep a constant velocity with the dragging of your mouse cursor. There are other things you can try. So I wanted to illustrate this simulation and really overall the PhET-Colorado.edu, the simulation website, because you can explore those on your own. Throughout this semester, I'm actually gonna go through these simulations and with each week's topics, if there are ones that are good to illustrate. If there are, I will do that. But ones I maybe forget to, ones that I don't think are all that interesting, but maybe you find it interesting. So the nice thing about simulation is you can explore it on your own. Thank you.